In this example, I want to introduce you to track cycling. Track cycling is exactly like it sounds. It's riding a bicycle around a track. Sometimes this has been called the NASCAR on two wheels. It's a small track, they pack a ton of cyclists on there, and there are plenty of crashes. Let's take a look. All these bikes packed into this small track with steep banks. They're traveling about 40 miles an hour. There are no brakes on these bicycles, and a lot of crashes happen. Just crazy. So to set up this problem, let's take a look at the tracks. So the tracks have tight corners with a radius of about 20 meters around these corners here. And they're traveling about 40 miles an hour, which is about 18 meters per second. Now, if these tracks were completely flat at this speed, it would require tremendous amounts of friction in between the tires and the ground to be able to make this tight turn. So to alleviate some of that friction needed, we have these banked corners. So you can see how steep that these corners are banked on these tracks. My question for this scenario is, if we're heading around a corner that has a radius of 20 meters and we're traveling at a velocity of 18 meters per second, what bank angle do we need here so no friction is needed between the tire and the ground, making it safer for riders? If this bank angle becomes too steep, the tire must provide a frictional force up the incline. And if this angle's too shallow, the frictional force would be down the incline. So we're looking for this perfect scenario where no friction is needed between the tire and the track. So let's go ahead and get started with this problem. So I'm going to pick a coordinate system. And the coordinate system here, I'm going to say up is y. And to the inside of the corner, right, where we're accelerating, I'm going to call that the normal direction. The normal direction with the letter n. So let's first sum the forces in the y direction and set those equal to 0 because this rider is not coming off the track in the y direction. All right, so what do we have? Well, this angle for n here, that is also equal to theta. So remember that angle is theta. So in the y direction, we have negative w downward, and then upward we have a component of n, which is n cosine theta, and then that is equal to 0. And now let's simplify that for the normal force. N is equal to w over cosine theta. Okay, we're going to need that later. Now let's sum the forces in the normal direction, and that will equal the mass times the acceleration in the normal direction. And remember that the normal acceleration positive is to the inside of the track here. Okay, so let's do that. So the sum of the forces, well, we just have this n component, which is n sine theta this time. And that is equal to the mass times the acceleration in the normal direction. So where do we go from here? Well, we know what n is. So we can plug in n, so we get w over cosine theta sine theta. All right, just plugging this in for n. And the mass is then equal to the weight divided by g, right? If we're given the weight, we can divide that by g. And the acceleration in the normal direction is the centripetal acceleration. And if you remember, from last chapter, that's v squared over rho, where rho is the radius of curvature. So in our case, that's 20 meters. Now let's do some simplification here. The w's on both sides of the equation cancel out. Sine divided by cosine on this side is actually the tangent of an angle. If you remember, sine of theta over cosine theta is tangent of theta. And then let's just sub in some values here. So we have v, which is 18, and let's move down a little bit, 18, and then we have rho, which is 20, and then we can't forget about g. We have g on the bottom as well, which is 9.81. All right, simplifying that, we come out with tangent of theta is equal to 1.65. And then solving for theta by taking the inverse tangent of that, that comes out to 58.8 degrees. So for no friction on this tire, between the tire and the track, we would need a bank angle here of 58.8 degrees. That is very steep. If you think about your staircase in your house, your staircase is usually around 35 to 40 degrees in terms of the angle that it inclines. This is nearly twice that. So this is a very steep angle that you need here on the tracks. And by the picture that you saw previously, that makes sense.